Okay, welcome to this video in which I'm just going to discuss quite briefly the concept of hard and soft nucleophiles and electrophiles. You'll remember from the first video in this week's set of lectures that I discussed the two important types of interaction between nucleophiles and electrophiles that are attractive forces that bring the molecules together for reaction. The two were, firstly, electrostatic attraction between the molecules, and secondly, orbital overlap between the HOMO of the nucleophile and the LUMO of the electrophile. Most reactions involve a combination of both of these, but it's possible for one or other to predominate in the reaction of two molecules. And which of these factors dominates actually depends on the type of nucleophile and electrophile involved in the reaction. And it's understanding this concept that's key to understanding the difference between hard and soft nucleophiles and electrophiles. So let's get straight into it. Nucleophiles containing small electronegative atoms such as oxygen or chlorine tend to react predominantly under electrostatic control. So that's the electrostatic attraction of the two molecules that come together. So nucleophiles of this type tend to be defined as hard nucleophiles. Nucleophiles containing larger atoms, sulfur, phosphorus, iodine, and selenium, they actually have larger, more diffuse orbitals, and they tend to interact with other molecules predominantly by orbital overlap. So large nucleophiles like this tend to be referred to as soft nucleophiles. So if I put a table up that summarises the key types, this isn't a table to learn, this is just a sort of a guide to the types of hard and soft nucleophiles we see. If we look at top left of this table, nucleophiles like hydroxide anions, alkoxide anions, the chloride anions, small molecules with negative charges, these are going to react predominantly under electrostatic control. These are hard nucleophiles. But you'll see hard nucleophiles don't have to be charged. Again, we've got nucleophiles here, water, alcohols, ethers, ketones even. These are nucleophiles that are reactive via lone pairs of electrons on the oxygen. But again, oxygen is a small electronegative atom. Electrostatic attraction is going to be a big factor in these nucleophiles reacting with an electrophile, and similarly with things like amines or organometallic molecules like Grignard reagents or organolithiums. These are all examples of hard nucleophiles you'll see in this module. Soft nucleophiles, very commonly you'll see are sulfur-containing nucleophiles in this module, so things like thiolate anions, selenide anions, but also some of the larger halogens like the iodine anion is a very good and soft nucleophile. Similarly, thiols, sulfides, phosphines, these are soft nucleophiles. And also, as we've seen in previous lectures, alkenes and the pi electrons and aromatic rings can react like nucleophiles. These themselves will be quite soft nucleophiles because their interaction with the electrophile will be predominantly under orbital overlap control. And that's really it, that's the key differentiation. So we can say that hard nucleophiles typically from the early rows in the periodic table, so these tend to be smaller atoms that have high charge density, whereas soft nucleophiles, as you move down the rows, they tend to be bigger atoms. They're typically from the latter rows in the periodic tables that have uncharged or larger atoms with higher energy, more diffuse orbitals. Remember, the further away an electron is from the nucleus of an atom, the higher energy it will be. So when you have these soft nucleophiles with these big orbitals, with the electrons quite a long way away from the nucleus, these are going to be high energy orbitals that the electrons exist in. And you can categorize electrophiles in the same way. So for example, a proton is a very hard electron, it's a very small atom, and it's charged. Whereas bromine is a soft electrophile, because again, bromine is quite a large atom, there's no charge, there's no dipole, so any interaction of bromine with a nucleophile is going to be under orbital overlap control. So you can categorise nucleophiles and electrophiles as hard or soft. And I thought the best way to actually explain this was to introduce you actually to a new type of electrophile that you have yet to see, and that is an alpha-beta unsaturated carbonyl. So the alpha-beta, that means that there is unsaturation, i.e. a double bond between the alpha and the beta carbon of this molecule. And what that means is, relative to this carbonyl, so this is the carbonyl carbon, if you move away from the carbonyl along the chain, you can label each atom using the Greek alphabet. So the first one is the alpha. So relative to the carbonyl, this is the alpha carbon. And the next one along, relative to the carbonyl, this is the beta carbon. So what we're saying is between the alpha and the beta carbon, there is unsaturation, i.e. there is a double bond. And when you have an alpha-beta unsaturated carbonyl, hopefully you'll notice from the previous lectures that these two double bonds are conjugated, and that means that this electrophile has quite a key distinct feature, that being that there's actually two sites within this electrophile that nucleophiles can attack. That's the key point. So nucleophiles can either adhere directly at the carbonyl carbon, or via conjugate addition they can attack this carbon. And this is therefore a nice system actually to explain the difference between hard and soft nucleophiles and electrophiles. Because if a nucleophile is to react at this carbonyl carbon, this is where the largest dipole is. This is where the most electron poor carbon is, because this carbon is closest to the electronegative atom. So any interaction between this electrophile here, specifically this carbon, and a nucleophile is going to be governed by electrostatic attraction. So electrostatic attraction is greatest at this carbon because it's closer to the electronegative oxygen, so this is actually quite a hard electrophile. Whereas if we look at the other electrophilic centre of this molecule, so that's this carbon, the beta carbon here, so I've drawn the molecule in a different orientation. If you look at the lowest unoccupied molecular orbital for this conjugated system, the atom with the largest coefficient in this molecular orbital, effectively the largest antibonding sort of orbital lobe, is actually this beta carbon, the carbon at the end of this conjugated system. So any nucleophiles that will react here, the interaction is going to be largely governed by an orbital overlap. So we can actually say that this other electrophilic site in the alpha-beta unsaturated system is quite a soft electrophile. So hard nucleophiles will selectively add to the carbonyl carbon, so something like this methyl lithium here, this organometallic reagent, that's a hard nucleophile. It will be electrostatically attracted most strongly to this carbon, therefore the nucleophilic addition will take place here. Whereas if you have a soft nucleophile like this thiolate anion here, that's actually going to have better orbital overlap with the beta carbon of the conjugated system, so it will adhere through the conjugated system, the electrons still get up onto the oxygen. This is a conjugate addition, and it will happen here because this is a soft nucleophile, because it's got a sulfur with a large atom with high energy diffuse orbitals. That's going to have more effective orbital overlap with the soft beta carbon. You'll get conjugate addition. So you can differentiate between hard and soft nucleophiles and electrophiles within this one system, this alpha-beta unsaturated system. One thing to say is if you do have an alpha-beta unsaturated carbonyl like this and you have a nucleophile adding to the beta carbon, this is a conjugate addition because the additions are occurring through the conjugate system, the electrons are ending up on the oxygen. But more importantly, this is called a Michael addition. This is a reaction you'll see in the carbonyl chemistry lectures. So just to summarise, hard nucleophiles are small, charged nucleophiles. They tend to be quite strong bases, i.e. weak acids. The electrons on these small atoms will be low in energy because they'll be closer to the nucleus, so they'll have a low energy HOMO. And when you're looking at the alpha-beta unsaturated system as an example, they will prefer to attack directly at the carbonyl. So think hard nucleophiles, we think of things like alkoxide anions, azide anions, organometallics like methyl lithium, things like that. Whereas soft nucleophiles are much larger, they tend to be neutral, they're not particularly basic, because the electrons are in large orbitals that are quite a long way away from the nucleus. They tend to have quite high energy HOMOs. And if you're comparing reactivity in alpha-beta unsaturated systems, soft nucleophiles will prefer to add to the beta carbon through a conjugate addition. And the key sort of examples of soft nucleophiles we tend to see are things like thiolate anions, the iodide anion, phosphines, and so on and so forth. So hopefully that gives a nice explanation of the difference between hard and soft nucleophiles and hard and soft electrophiles. Cheers.